Thank you for the invitation. And I have seen like people here, there is less audience generally. I see lots of students here. I feel encouraged to talk. And little bit about my background. So I had my bachelor's in information technology, and then I moved over to remote sensing and did my PhD and then postdoctoral studies. So you can expect some jargons or terminologies coming from AI like machine learning models or little bit on the geospatial side. If you don't understand, pardon me, but I will try to keep it simple. And we will talk about agriculture, how Geo AI is trying to fit into this domain, and there are many opportunities, many challenges coming up, and a few case studies that I have been involved with, some that I have led here in Texas A&M, and how are we going to move forward with this kind of opportunities, challenges, and the new era of, for example, AI and the way they're used to streamline, automate the different tasks here. It's morning time. Sometimes the kids may be waking up and making some noise. So yeah, I'm hopeful they don't get awake. But let's see. So my research presently involves using a modality of Earth observation data. Modality in the sense, in general sense, modality means, for example, text is a different data, audio is a different data, video is a different data, all those kind of things. In remote sensing, generally we refer to, for example, multispectral data as a different modality, and microwave data is a different modality, hyperspectral data is a different modality, right? And the vector data, all these kind of like different styles of observation, we refer to as different modalities. So I'm trying to use them, and the focus is on in-season mapping, in-season crop mapping, in-season yield prediction, in-season estimation of water demand, and modeling the growth behavior of crops. Because whenever you do it on time, it basically matters. For example, for insurance, for decision making, for everything. And of course, there is a climate resilient agriculture thing which is coming up because more and more carbon emissions, nitrogen emissions, methane emissions are being studied. So this has become another important area where people want to know how much basically we are emitting from these agricultural fields. So we talk about opportunities. Globally, if we see the adoption of AI is rising significantly, and we can see like in the US, it's expected to raise up to 4.7 billion by 2028. And if you see the global numbers, it can grow up to like 6.9 billion in 2035, and it can definitely go up in India too. India has been really proactive in investing in AI in agriculture. You can see like they're earmarking 10,300 crores of money to build robust AI ecosystem. So we see lots of potential for us to, for example, get nice projects to work on, nice research projects, nice jobs wherever we are in the world. So like farming or agriculture is a very major sector, and there is nothing which is going to limit this, right? So we need to be ready, and we need to understand how big this market is to, for example, if we have some research interest, how we can go about it and build our career. So what Geo AI can give here is basically in-season automated pipeline that ingest satellite data. So it means that the satellite data should be automatically pulled in. No need to download data or anything, right? Detects fields, models growth, and predicts quantities like yield or biomass or anything. So right from the beginning, whenever we say satellites, we understand that there are a bunch of them above above us and observing everything. And we understand that how much data is coming in. There is also a data which we think, okay, it's enormous and we cannot manage on our computers. We need computing power, we need storage power, all those things are coming up. At the same time, there is thing called like cloud computing. There is a thing called edge computing. Edge computing means like you have devices which are computing, like which are running real time and generating some outputs, right? And cloud computing, like computing is done over the cloud. You don't need to spend your own hardware resources to do the computing. It's done over some cloud platform, and you just pay for it, or sometimes they're free. So the challenges are that ground data collection, for example, even drones or LiDAR, they are not very feasible for regional scaling. You can do it over multiple farms. If some scheme is launched or do it for the whole nation, it will be once, for example, in 5, 10 years, and you can't cover at scale. And also regularity is very difficult. And with satellites, because they revisit all the time at a regular interval, you can definitely think of monitoring during regular intervals every season, because you got data there. But the problem is remote sensing datasets are also temporally, spatially, spectrally, radiometrically misaligned. So you can have data which is, for example, 10-meter resolution, 30-meter resolution, 3-meter resolution, 50 centimeter resolution, and they can go to different resolutions. And spectral also, like the bands, they may not be the same for all the satellite missions when you are using them together. Infrared or near infrared might mean something else for one satellite mission, a slight difference might be there for another. And radiometry, like 8-bit images, 16-bit images, 32-bit images, it can differ. And temporal mismatch is a common thing that you see, like one satellite is flying today, another you can't get data today, you have to wait, for example, 2 3 days. So this mismatch of 2 3 days can also result in differences when you are trying to model them. And a wrongly directed field, for example, if you are trying to develop a pipeline that automatically detects a crop field, predicts the future growth curve, and does the prediction of yield or something like that, if the crop field detection is wrong, the whole process is going to be wrong. So there is a thing called the mixed pixel problem. If we see the upper image here, it's a sentinel-2 image which is 10-meter resolution, and you can see like the field is pixelated. It's a crop field, by the way, it's a cotton field, and you can see the pixels pixelated. There is a road going on here, and you can't see much from here. You don't understand, though the computer can understand, but we cannot. And then there is this planet scope image which is 3-meter resolution. Still things are a little clearer. You can see there is a agricultural field here. Then there is a 50 centimeter resolution planet skysat image. Now you are getting more details, and I am showing this on a slide. You can zoom in, and then you can see, for example, a cotton plant here, right? And the last one is a UAV image, which is a 2 centimeter image. So here you can zoom in and even see a plant directly, leaves also. And this is possible with ground data, but unfortunately you cannot scale it everywhere. So we are thinking of ways how satellites can do this. So I'll present three case studies here. The first one is in-season crop mapping for data scarce regions. So the objective here was, there was a USAID project for which we were collaborating with teams in Armenia. So the country had less amount of data because they had been through wars, and there was not ample resource, either human resource or other types of resources to go and monitor fields. So basically, we were bereft of any kind of training data to do modeling. A few data sets were available. So our plan was to basically do large scale mapping of wheat fields, winter wheat fields in Armenia. And the objective was to first train the models using rich data sets in the US Midwest, somewhere around like Kansas, and then transfer learn using the limited samples that we have in Armenia, using multispectral satellite images, and then the final model gets deployed for Armenia for the new season, or whatever it's going to detect in season winter wheat fields. And you know that it contributes to Armenia's GDP, and it's really important for them to do the nationwide identification of wheat fields. This is how the US fields were, for which we have training labels. So one thing is training input. Training input means you're getting it from, for example, satellite images, and you are feeding them to the deep learning or machine learning models. And there is another thing called training labels or training targets. So they come from ground truth. Basically, somebody has to tell this field is a wheat field, this field is not a wheat field, something like that. So in this case, a US Department of Agriculture has their cropland data layer, which releases their data, for example, every year. They don't have data for 2026, and I don't think they released for 2025. So it's still important to classify crops during the season, because USDA might do a lot of verification and then come up with an accurate data set, but and they're still not up to doing it every season and during the season. And there are a lot of research going on. There are people who are doing this, and it's very exciting to see the results also. So for this we had 2024 data, and the labels were generated from USDA CDL, and we know that this can be used for training, and later on the model can be deployed for new years. So that's how we went. So we did train different styles of model based on learning temporal features, spatial features. So a pixel that is a winter wheat crop pixel, neighboring pixel is also supposed to be that, unless you have an edge or something on the field. So you identify fields based on that. Also temporally, the crop growth curve defines how it is a crop. For example, a winter wheat curve might have a double sigmoid style of winter growth pattern. A cotton field might have like a log normal style of growth pattern. And similarly, sorghum and other crops might have their own signature in time. So, using those time series of images, we try to kind of map and tell the model that this is how the behavior, the temporal behavior is, and you should try to see which fields or which pixels belong to this style of pattern or this style of crop growth curve, and then classify them. So I'm not going into the details of these models. LSTM is generally useful for time series classification regression problems, and UNet and SegNet are image segmentation models, and there are a bunch of them going on which take images as input. Time series of images we use here as input, and to divide the whole image into patches is required because we have limited computing power. We want to do it parallelly, so it has to be fast. So once we do that, transfer learn from US, then a few samples in Armenia. This is how we are going to get our final results. So if you see the images here, these are four images as input to the model. Also one image deliberately kept as containing clouds, and this should be the output. This is the ground truth. And we see the models. Models are almost very accurate in detecting all the winter wheat fields, if not like almost all, if not some are left behind. And using these models, we go to Armenia, and the few samples we use, we try to see whether they are detecting it rightly or not. And then we grow to larger regions, and we try to identify where are the wheat fields. And at the end, we basically do it for a whole province there in Armenia. This is called the Shirak province, and different models do this. And we found out that LSTM was the best one for Armenia, and we experimented Sentinel-2 and PlanetScope images. Sentinel-2 is open access, 10-meter resolution, which did very well for the US and was not that great for Armenia, where we did transfer learning. And PlanetScope images, they performed really well in both the cases, and we got like very nice estimations of the overall planting done, overall like acreage of winter wheat that year. And we did it for 2 more years, and the results were matching with the reports that we have from different sources, for example USDA or some UN report. So extending this idea, we also did mapping or attempted like mapping of cotton fields. in Texas. So Texas is a state where I am presently living and working, and cotton is a very prominent crop here. World's largest production of cotton happens here in Texas, almost like, and in one of the regions, it's like 80% of the world's cotton is grown. So we wanted to do large scale mapping of cotton fields, again using not the multispectral satellite, but a mix of different satellite observations. So this is probably how a cotton field looks like. This is near to our research lab, and this is where Texas belongs, the whole state, and these the markings are the different counties in the state. So we start doing this, and we try to use only 3 images or 4 images within the season. Month-wise, one image per month is good for us, so that we can monitor the temporal dynamics, and then we try to find out how the model is going to do. So this is how we go. USDA cropland data layer will provide the labels for us, and then we use Sentinel-2 multispectral, Sentinel-1 SAR data, and we fetch it from Google Earth Engine, and we try to do the filtering of the multispectral data, which has clouds. We try to remove them. Then we do matching, and then we feed the data to this simple type of models, LSTM, one dimensional CNN, gradient boosting, all those random forest models, and basically predict for a new year and new sites. So once we are done, we can do yield forecasting with the known crop fields, and we can upscale to different regions. So we did that. We had these different regions, the training counties, and we used different modalities, optical and SAR, and we created data sets from March to May and March to June, one image per month. And the cropping starts like February, end of February, it ends around like August. So in February, you don't see anything, especially because of the mixed pixel. The mixed pixel problem is the image is not able to distinguish between soil and canopy or vegetation. So it is in the early stages specifically, it doesn't distinguish the soil or vegetation properly. As soon as the vegetation grows bigger, then the images are able to see that, oh, there is vegetation on the ground. So that is why we are not using any image in February, and generally the linear peak phase of the crop growth curve is more important, because that determines how the yield is going to be, how the biomass is going to be. So for that, we are just using these monthly composites, and we used around like 20,000 labeled sample points. And these colored regions are basically the cotton growing regions of the Texas state. So if you see this has been the behavior. This is the famous normalized difference vegetation index. And if you can see, this curve is a little bent. If you see the average is a little low, while the average is a little high. The timing of the peak signal is also different. That also governs how the growth is going to be. So there are many things in temporal data. The timing of the peak season, when it starts to grow rapidly, when it's going to senescence, when it's going to be stabilized, and even during that, whether there is rainfall that is affecting, how is the temperature, all those things usually determine how the crop is going to be. So we are using a combination of physics informed features here, like physical vegetation indices and all those things, and try to do something. If we see, I've just marked a red dot on wherever a field is identified here. And if you see, the yellow boundaries are the actual fields, and if you see, most of the fields were correctly identified here. So it means that if you have good training data, generally your model is going to do well. If you see, like, this is another region of the state. It's going like northwest, and this was southeast. This is CNN outcome, this is LSTM outcome, and mostly if you see, the dots are lying inside the crop fields. They don't go out anywhere. So which is very good. You just pass an input, and you will be ready with the crop fields. You know them. Boundary delineation is easy once you detect where the fields are. So simple model like random forest can also detect fields you don't need very heavy models to do, for example transformers or anything like that. The problem is easy. The difficult part is you need to get images on time. Also, you need some training data for modeling these problems. So way forward is we are trying to transfer to other crops and other regions of the US, and then operational large scale deployment. And once we do it for the US, we'll go beyond and do it for other major countries. Of carbon from agricultural fields are also an important contribution, and we planned a way in which we had the ground flux towers data that the team has. The collaboration is going on with a team at like Texas A&M University College Station and partners. They are being mentioned here, and they have these flux towers. They go set up these flux towers which monitor the emissions of carbon, nitrogen, methane. Also, they have the soil moisture chambers to monitor how the moisture is varying throughout the cropping season. And the ground data is really nice. We get the results, but the problem is you can't get results for anywhere you don't have the flux tower, right? And you know that you cannot do it everywhere because these eddy covariance or flux towers, they provide net ecosystem exchange. Ecosystem respiration and another factor, right? So this is basically governed based on how the plants are taking carbon, how the environment is behaving with respect to that, right? And the gross primary production, that was the other factor. The gross primary production is subtracted with basically the ecosystem respiration to determine what is the net ecosystem exchange, or more openly if you say it's net carbon ecosystem exchange. So we are trying to see whether satellite data can do what the ground data is doing. It's not very feasible, but it's like a rough idea. And there are also a bunch of towers set up everywhere in the world, especially in the United States, except these separately owned flux towers, which are going to create like a network of flux towers, like FluxNet they call. And they can also help get a good training data for learning, and also like a dense network that can help people. So we know that carbon budgets remain uncertain at present because we don't have a regular or a continuous dense network of observations. We actually have sparse in situ observations, and the existing models they generalize. They fail to generalize, sorry, according to different sites and crops and climates. So as soon as you have different sites, you change the crops and the climatic condition is different, the models will fail. So there is always a need to generate scalable data-driven approaches that could learn from limited data, limited in situ data, and then use satellite information, remote sensing, or climate information, and they try to find out the emissions. So this was the objective. The objective was to predict daily net ecosystem exchange observations. This has been kind of successfully done for the US Midwest. We have found some papers, but it hasn't been done for Texas. And also, there is always scope. For example, the study that has been done gives 250-meter resolution data, daily data for the Midwest, and you need to do it every year. And here, the fields might be a little smaller. Also, if we want within field information, within field variability, 250-meter pixel is not going to help. So we used different fields. We used 8 fields here for this study, and the crop types were different, like sorghum, cotton, corn, rice, sunflower. And we had the team has set up the flux towers to get the in situ measurements. And after that, we are trying to derive the satellite information. This is how the field instrumentation looks like, and this is how the field data looks like. It's nice. You have like a pattern of what's happening on the ground, you know how it should vary, and you can see the variables also, positively or negatively, they have a nice correlation. So we just downloaded whatever is open access from the Earth observation wind data and so on, and we tried to do this thing for the daily time step. That's how we are trying to model this problem. So two different approaches. One uses in situ data. All this is available from the flux towers, and the other approach is using only satellite data. And both go into the model, and then we try to evaluate or validate the model using different strategies, and then see whether the satellite data-based model is coming anyway close to the in situ model. Is the results with the in situ data a very high correlation with the ground data? If you see, and this is the crop growth curve, right? You see like very strong correlation, and the mean square errors, RMSE values are also within range. So and these models are not very huge deep learning models, these are simple models, because you decide a model based on the data. And when we use satellite inputs also, slight decorrelation or like slight bias here. The model is not able to predict something going down here, but it's doing well. The other model is doing well, and MLP is showing some rise here, but random forest is doing good here. It's picking up the fall. So the satellite measurements also go near. They need to be calibrated based on more data. They need to be refined based on more and more data. But overall, if you see, it's a very promising result, and we can definitely improve the models and then make them work very near to the flux tower data sets. The best advantage would be you don't need flux towers. After you have these satellite data sets working for you, you get data ingested every time you have new data, and then you can do this you can do this like carbon emission modeling. Similar to this, you can go for like nitrogen emission modeling based on how and what kind of information do you have. So my third case study was based on representation learning side. The studies that I have shown now or just before are based on, for example, Sentinel-2 datasets or even coarser datasets like climate dataset is gridded climate data 0.25 by 0.25 degrees. You have got one value, still useful to do some kind of modeling. But for precision agriculture applications, you definitely need, for example, 3-meter resolution pixel, or at max you can go to 10-meter resolution, because you want to know what is happening in the field exactly, and you want to design or you want to take decisions based on what is happening within the field and not like something given for the whole field. So why canopy volume? It's an indicator of crop growth and productivity. It's usually linked to the yield. So by modeling canopy volume, you can definitely know how is the biomass, and the canopy volume is a function of canopy cover and canopy height. So canopy, you can simply assume vegetation or crop. Crop cover means how much the crop is spread within a grid. For example, if you take this grid here, this much will be the crop cover. Or if you take this big grid, then you have, for example, 50% crop cover. And then canopy height is like, for example, every crop differs. Sometimes the highest may be 80 centimeters, sometimes the highest may be like 60 centimeters, sometimes 1 meter, something like that. So if you can somehow monitor this canopy volume, which is dependent on like width and height, canopy cover and canopy height, basically you can predict the yield, you can predict the biomass very nicely. And the geospatial community has washed its hands with the studies based on forest canopy volume estimation, which has a very uh, loose, or you can say like very liberal margin of error. You can go wrong, for example, if even if you have errors in height measurements around 1 to 2 meters, that's okay, because in forest you have tall trees, and you can go in uncertainty in the spatial side as well, and you can still assume how much of carbon is being taken up, how much carbon is being emitted, or for example how much is going to be the biomass. But as soon as you go into the field, then you start having problems. Then the model fails to generalize across time, crops, climates, all those things. So you need something that can do within the field, the first thing. And how you can model, because there are multiple things that govern, as I told, like the weather, climate, the rainfall data, the crop growth pattern, the soil, and how the things are going within the field. How is the field? Certain parts of the field are productive, certain parts of the field are not productive. So based on that, you have to decide and you have to model those, the patterns. So the objective here was to estimate UAV scale carbon canopy volume using satellite data. So you now, but the problem is UAVs cannot go everywhere. It takes time, it takes human effort. So this is how the study area has been. The area is like near South Texas, a field called Driscoll, and I used training for the years 2020, 2021, 2022 as training, and for test I used 2023. And we have RGB sensors, red, green, blue bands, and multispectral sensors flown at 80 meters altitude. So this is how the UAV data collection has been planned. So you can see there is slight irregularity based on the weather, based on the availability of staff, and how the weather goes and everything. They plan out, okay, we go and collect data today. So we have a very nice data set, but it cannot be scaled everywhere. But this study definitely helps connect the satellite inputs with the UAV inputs and try to model the way we can do it with UAVs. So these are the multimodal inputs again. UAV data becomes the ground truth, only used for checking the accuracy. It doesn't become input to the model. And input is planet scope data. We are generating NDVI, green chlorophyll index, which can give us the spatial variability. Sentinel-2, red, green, blue, infrared, and Sentinel-1 radar, VVVH, VV by VH ratio. And we generate canopy cover data using the software that we have here, Metashape, like licensed version, and then we generate canopy height separately using like some digital surface model, and then we multiply those to generate canopy volume using this pipeline, and then we make a grid. So this data is 2 centimeter. We create grids of 9 meter so that it can relate to satellites, and then we generate like mean reflectance and mean and standard deviation from the satellite data, mean backscatter from radar, and then we try to do temporal matching to see, okay, whatever matches within 2 3 days of observations, and then generate our training input data for the models. This is how the variability is during the season. So it reaches some peak phase, then it falls down, and these are the curves of NDVI and GCI. So there is some connection. And if you see the modalities, this is Sentinel 2 data, the blue one, and Sentinel and the Landsat data, the 30-meter data is orange one. This is how the precipitation data is. This is how the radar data behaves, VH band, and this is how the evapotranspiration data is. So they also tell, the modalities also tell, and they, when they go into the model, they mean a lot. We might not understand anything from here, but the model uses them to detect certain patterns. This is how the radar data behaves. Generally, we don't see much from the visual, so I'm plotting here the spaghetti plots, that you understand how radar data can also give you different patterns. So this is the methodology. We try to do spatial harmonization using zonal statistics, and we download weather station data also, and we generate something called as a heat units. Heat units is a technical term in agronomy. They try to find out how the temperature varies, and they generally go by cumulative heat units so that they know how much cumulative heat units generally are required when there is a peak phase, and how can which duration of the crop growth curve should define how much of the growth has happened, or how different stages are behaving, for example flowering and all those step of all those stages. So this data that we have, the other way is to first generate embeddings from this input data and then pass the embeddings to the model. So all the foundation models nowadays, they're working on these embeddings. So they basically use lot of earth observation data, but instead of using all the bands directly, they compress them into something called as a latent space or embeddings. And these embeddings basically contain useful information, but they discard all the redundant information from the data. So you have lighter data now that allows you to have more and more training data from different parts, and then you can use all of these embeddings basically as input to the model. And it's still getting experimented. Google has this alpha earth model, and there is also a prithvi model, and lot of foundation model stuff going on. So we are also trying to generate this representation learning from these embeddings. So these generates two hidden layers here, and they generate a 32 dimension latent canopy embedding, and then it goes as input to the model. So if you say it's a two-stage learning, one is learning of embeddings, and then you are trying to regress canopy volume from embeddings. And if you are good, you can predict over new sites. So this is how the relation is between GCI and canopy volume, NDVI and canopy volume for different dates, colored by different dates. So the relationship is worse during early days, and it gets correlated thereafter. During the peak phase, it has a good correlation. This is how the results are. So you see the baseline models, there is no embeddings used here. They're still doing okay. There is no such problem. There are a few outliers going, and this is the ridge regression model which is failing, like in to model these some of the few points which are not fitted properly. But if you see the test data, the ridge regression model behaved the best. So this is somewhere like near 60 days after planting, or a little far than that. But as soon as you grow in the season, the model is picking up very well. It's detecting the canopy volume from the satellite inputs that can match actually the UAV ground truth. This is how the whole crop growth curve will look like, and that's how we are trying to generate the multimodal ensemble performance and trying to match it for different dates. This is generated from Planet and Sentinel-1. This is generated from Planet, Sentinel-1 and Sentinel-2. Slight improvement when we use different modalities. And effect of embeddings, if you see, there are more points coming in on the other side of the curve here, and they disappear when you use embeddings. And there are still a few things going on. This was very little data only for one field, but we are going to generate a lot of training data from these satellite data sets, because embeddings don't need any ground truth. You can also generate these embeddings and use a decoder. Basically an encoder will generate embeddings, you use a decoder to see whether it's reconstructing the signal properly or not. Then you can use this encoded data to see whether it fits the time series, some missing time series or not. These are certain ways in which you can still understand whether the embeddings contain information or not. So as far as you have good information, you can do very good downstreaming with that embedded data set. So we are trying the plot. Each of the line defines how a pixel is behaving, certain part of the field. Then we also tested the effects of using heat units and not using heat units as input to the model. And we could see that okay, without heat units it's causing a bend here. With heat units it's kind of continuing, which is more useful. So we understand that heat units can be a useful input, and we can get this information, though not very high resolution, but we can know it for the whole field, and then that helps how the growth will be defined. So we know that planet data is like 3-meter resolution, it dominates the signal, but to be informed, we know that this data is not free. This is provided like a licensed version for a month, and you have some limit on the download of the data. Sentinel 2, Sentinel 1, the NISAR mission is coming up. It's a like Indian and US combined mission that is going to provide free data to everybody. So my planned future research, one way is to do multimodal data modeling to optimize crop monitoring and management. The whole pipeline you can see here. So I'm trying to generate some ground truth using UAV, and then I go to satellite data sets. The weather data sets come from some sources, soil data sets come from some sources, and then I generate encoders, or I generate these embeddings using different encoder models here. These may be temporal models or something like a CNN or something. Generate these embeddings. These can be like transformer models also based on the volume of the data. And then they go to another model. This is this model is going to do a downstreaming. Sometimes they're just used as a regression head. So we are trying to generate something that is generated from the UAV, which is called cropcast. So it tries to forecast the rest of the season based on whatever input it has during the season. And once you have this forecast ready, you basically have the full curve, which can help you get the yield, which can help you do probabilistic modeling, decision making, and so on. So this work is, for example, cropcast. This is how we are trying to model, trying different inputs to the model and seeing how much it can forecast. And up to now, we are seeing very promising results. We can see how the model is behaving very well. It's trying to predict or forecast the curve within the season. This becomes really, really strong evidence. And then if we use it for decision makers, for farmers, for producers, telling them, oh, this is how it's going to be, they can determine how the yield is going to be very early. And if they can sell early, they can have more profits. So this is how we are trying to do. And based on the forecast, we can do the yield predictions, and we can know how it's going to be at a certain time, when we need it basically. And that helps in also understanding the economy part, how many dollars or how many rupees you are going to get per region of your crop. It goes to that level. So another research that I am part of is the Texas Climate Smart initiative. As I told, they are trying to investigate the effect of climate smart practices. So they are basically funding farmers to adopt climate smart practice. So whether the climate smart practice was adopted or not. This is kind of a workflow that I am designing, and we are using again the modalities, trying to model them using temporal spatial behavior, and develop a portal where you can know real time how it's happening. That's how the portal would look like. Presently, like, it's under development. And there is another study that I'm doing with regional evapotranspiration and crop water demand forecasting. So based on the SAR data, we are going to get information on soil moisture, and they go as input along with ET data, evapotranspiration data, into a GraphCast model. And we are going to predict the future, for example, 15 days of evapotranspiration. So there is evapotranspiration data, daily data available now, but we don't know about the future. So for decision making, we basically need to know what is happening in the future. So through this model, which uses, and we are basically proposing NISAR for that. Like, we'll use NISAR data, and we are going to use this ET data from open ET or sources like that at 30-meter resolution or something, and we are trying to forecast it during the season, the crop water demand. So it's in collaboration with Kansas State, Oklahoma State, and Texas. So if we go by the acknowledgements, these are the co-authors of the study. The producers need to be acknowledged. They provide information on their farms. These are the collaborators and all these different partners that we are working with. And to end, these are my two little ones, the two little kids who are presently sleeping. Wanted to say thank you on a lighter note, and I'm thinking whether they can become my probable future partners in my research. Let's see how it goes. So yeah, I am open to discussion, questions, and my email is there if you want to write to me, you want to work. There are many things coming up. Thank you.